We're going to explore that a bit more. If we have a circuit and it looks like this, or we have our battery, down here this is minus, this is plus. We have current coming around like so, and this is a resistance. It has a current going through this resistor, and it has a voltage across there. We can look at this resistor and say, oh, well, let's consider the energy being produced by the battery equaling the energy being consumed by the resistor. Now, watch this. This is the conservation of energy. This is that law of the conservation of energy. We know that if we take the change in these two, we'll end up with a representation for the work because of the work energy theorem. Change in work is equal to change in energy. Okay, so if we just divide these by time, we'll end up with P delta V equals to PR. That's the power being produced by the battery is equal to the power being consumed by the resistor. So since we have that, we can rewrite that to be representative of I times delta V. This is the current in the circuit times the voltage coming from the battery equals to IR times VR. Now, whenever you have a series circuit like the one that was just drawn, that means that everything follows one another. I mean, it just is back to back. We know that the current is equal everywhere. This implies that delta V is just equal to VR. So the voltage produced by the battery is equal to the voltage consumed by the resistor. So we're going to use this idea So if we have this connected to a battery, minus, plus, we call this delta V. Let's say our current is going around like so, conventionally, by convention rather. We have R1 here, we have R2 here, we have I1 and then V1, and then we have I2 and V2. We're just going to go ahead and use our power equation again. We won't write the conservation of energy, but this is the conservation of energy. Power being produced by the battery is equal to the power being consumed by resistive load 1 plus resistive load 2. Okay? So with this, we can write I times delta V equals to I1 times V1 plus I2 times V2. But we know that I is just equal to I1 is equal to I2 because of the kind of circuit. Everything is in series. So we end up with, or this equation implies, I should just say therefore, but I'll put therefore. Therefore, we can say delta V is equal to V1 plus V2. So the voltage being produced by the battery is equal to the sum of the voltages being consumed by the resistors. There are two resistors, and so we can always extend that. If we keep adding resistive loads, the voltage is just going to continue to increase. Okay. Let's see here. So now we want to use Ohm's law. This is ultimately where we're trying to get to. And Ohm's law looks like this. V is equal to I times R. So this implies that I times the total resistance in a circuit equals to I1 times R1 plus I2 times R2. Okay? Since we have this, we know that all of the currents pretty much the same here. So we can write RT equals to R1 plus R2. Okay, that's the theory that we're looking at. And if we keep adding resistors to our circuit right here, if we added another one, R3, and an R4, and an R5, if we did that, then we end up with this, R3 plus dot 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 plus Rn. That's our general equation. And this is the theory that we're going to be using to calculate resistors in series. And we'll talk about the theory of calculating resistors in parallel in a moment. So let's go back to the lab here. And you'll notice that we have question number 1. And so we're going to answer this question in just 1 second. Well, let's answer it in the next video.